Be happy. Oh my goodness. All right. Okie dokie. So some of these slides are like, oh man, I remember that. So hopefully that will be the case. So we talked about different types of chemical bonds. So remember, the chemical bond is the thing that holds the atoms together in either a molecule or a formula unit. Two types of chemical bonds. There's covalent chemical bonds where electrons are shared, or there's ionic bonds where electrons transfer. Okay. We're going to be talking about molecular compounds first, pretty much. So molecular compounds means that all bonds between atoms are covalent bonds. Electrons are shared. But remember that the electrons might not be shared evenly. So I handed this out to y'all. Okay, can't have too many. So these are the Pauling values, electronegativity values. Remember, the symbol for electronegativity is that thing that kind of looks like an X. Check out all these I got from me. I know, right? Just makes you want to come up and draw. So electronegativity is that's the Greek letter chi. Okay, so these are all electronegativity values. These are all chi values. Just to kind of remind you how this all works, and actually I have a slide coming up, but why not just kind of build it here? Okay, water, right? So what is the Pauling value for oxygen? 3.5? What is the Pauling value for hydrogen? 2.9? 2.1. Okay, so do you remember how this works? That the one with the higher electronegativity is going to draw electrons to itself. So actually, the way this water molecule works, and you're going to see the same convention coming up, is we said it's partially. Now, the symbol for partial is this. So this means partially. And I know it looks weird because, let's see, and it's kind of like a, that's actually the Greek, the lowercase sigma. Because we're used to like a sigma, like the E-looking thing.
Isn't that the delta? The lowercase delta?
This one?
Yeah.
Sigma?
Because I know like the lowercase sigma is...
I don't know. We'll have to look into that. So this is delta?
Yeah, I think so. And the sigma is, the lowercase sigma is... It's like...
Well, we're going to do some Greek here. We're going to check that out. I'll check that out.
Okay.
So this means partially. So what we do here is, since this is higher electronegativity, we're going to go partially negative, and we're going to go partially positive. So even though when we did Lewis structures, and you're going to have to remember Lewis structures, anytime you see a line there, that means 2 electrons, right? Okay, but they aren't shared equally. And we're going to see a picture here in a minute to kind of show that actually this is kind of swollen over here with regard to electron cloud compared to our hydrogen. I kind of think of it that way. Okay, and so we have the same thing over here where this is partially positive because we have the same tug of war. It's a tug of war for the electrons making that covalent bond. Okay, so I have some slides to kind of reinforce that. So the Greek letter chi means electronegativity, and it's the attraction of electrons that an atom has when it's bonded to another atom. Okay. Let's see, the higher the electronegativity or Pauling value, the higher electronegativity, the more it's going to hold electrons to itself. So since oxygen is 3.5 versus 2.4, that's why it's partially negative. And so one of the tasks that you guys are going to be doing with this first lecture part is to identify, looking at a molecule and kind of looking at how the individual bonds are, okay, to see what sort of things going on. Now, this is what we call, well, I better get ahead of myself. So electronegativity, it's like this. Okay, so what do I mean by this? So if you just take the group A elements, and there are some exceptions, electronegativity increases from left to right, and it increases from the bottom up. Okay. So your highest electronegative is like fluorine. Now, I say neon's not high electronegativity because guess what? Neon doesn't want to bond to something. Okay, when you get over here, these rare gases are like, I'm not playing with anybody. You have to play with somebody to have electronegativity. So this is trying to show you how the electronegativity values go. The higher it is, then greater electronegativity. And this is the sheet I gave you. Notice it's like, really? Why'd you do that? I mean, because like it says electronegativity decreases this way and increases this way. Well, why don't you just say it increases and increases? I know, right? Saying the same thing.
I have a question. So the negative, positive, that's relative to the other atoms then?
That's relative to kind of the electrons as they are distributed around that molecule.
Right. So if the
so this
oxygen,
is electron rich and this is electron deficient.
But if the oxygen has higher electronegativity, then it's negative, and the other one's positive relative to that one, right? Like if the oxygen was less than the hydrogen, then that one would be positive.
Right, exactly. And it's possible, like, you know, it doesn't take too hard. We could, let's see, oxygen's 3.5. Oh, what about oxygen fluorine? I don't know if this is what you were saying, but when if you get an oxygen and a fluorine bonded together, then this guy is going to be partially positive and this guy's going to be partially negative. Why? Because it's its Pauling value, its electronegativity value. Is that what you were kind of saying? Mm-hmm. I gotta, again, I'm getting away from the point here, and this kind of reminded me of what you were saying. If I take another water molecule and I'll kind of orient it on purpose this way, partially positive, right? Partially negative. This is the cool thing that water does. Different water molecules, we have a dot, 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 and that's your intermolecular bond. See it? Isn't that awesome? Why? Because you have a negative and a positive. It's actually what we call hydrogen bonding. So anyway, kind of getting ahead of myself, but I'm giving you a glimpse into kind of where we're going with this whole thing. Okay. Non-polar covalent bond. So a covalent bond is the bond that is between two atoms. Pair of electrons are shared. Now, what we've been talking about is a degree of polarity. Why? Because their Pauling values are different, and the higher Pauling value is partially negative, while the lower Pauling value is partially positive. What if they have the same value? Okay, a good example, see, I can't remember oxygen. I think it's got a double bond to another oxygen. No, that's supposed to be an oxygen molecule. This is O2. Okay? So, by golly, we look it up, you're looking at 3.5 and 3.5. So, what's your electronegativity difference? 0. Yeah. That's an example of a covalent bond, but it's nonpolar. It's nonpolar. Polar means you have a charge difference. Nonpolar, it's neutral. Okay? So you get a nonpolar covalent bond when the two atoms have the same electronegative values. They don't have to be the same element, though. You know, that's why it's fun kind of going to the closet and saying, what two could I put together? And I would have a nonpolar covalent bond. PB and lead and bismuth. Yep.
Okay, cobalt and nickel.
Cobalt and nickel. There you go. So you just don't go close to minus the ball. Right. Yep. Electrons are shared equally. Yep. Okay, so usually though, you're gonna, when you have atoms stuck together in a molecule, usually they're gonna have different Pauling values. So you will have a delta chi electronegativity difference. There will be something there. And so the one with the higher Pauling value will be partially negative, the one with the lower Pauling value will be partially positive, usually. And then we would call that a polar covalent bond. There's different degrees of polarity though. The higher the difference, the more you're like, oh boy, or there's subtle difference here, like, it's basically nothing. Okay. Then with the higher electronegativity, we'll have the larger share of electrons, partially negative. Okay. Now, it's possible that your electronegativity difference is so great that the dude with the higher electronegativity basically says, I'm not sharing, I am taking. An electron is transferred. Okay. And in that case, electron is transferred, then you have ions. You have an anion, to where an electron is transferred to, and you have a cation, where an electron is transferred from. And then those two ions can get together, but it's not called a covalent bond, it's called an ionic bond. And I was noticing on my slides here in a minute, I put that threshold, I think, in Chem 1, the way I learned it, about 1.7, delta chi, 1.7. I think that we put it here in OpenStax at 1.8. But this is kind of showing you where these dots would be the nuclei of those two atoms that are stuck together. This would be where electrons are shared. Don't they look like they're shared? And I kind of talked about the electron cloud is kind of the green, okay? Versus, okay. So specifically we're dealing with hydrogen and chlorine. So what do we have for their electronegativity values? See if I have it. So hydrogen, you told me, is 2.1? And then chlorine is 3.0. Okay, so which one's partially negative? Yep. So that's partially negative, like this says. This is partially, oops, goodness, partially positive. But electrons are shared. The delta chi here, remember how that works? What would the electronegativity delta chi be? Looking at these two values. So it'd be the absolute value of, I usually do it this way, 3.0 minus 2.1. Yeah, 0.9. Yep. So we can evaluate a bond like that. Yep. So now this is something new. In physics, and as I said, maybe I don't know if I can clear that sheet. So sorry, it's a little bit messy. But in physics, we do a lot of this vector sort of thing, where we're talking about the line is kind of showing the force, how's the strength. The length of the line is showing the strength of the difference, electronegativity difference. And the direction of the line is showing the direction of it. So arrows work great. So for this, we've got the beginning of the arrow is where it's partially positive, and the tip of the arrow is partially negative. So just keep that in mind. Maybe. So the tip of the arrow is partially negative. Okay? All right, because you're going to see that convention coming up. So to kind of recap, this is a Chem 1 thing. We have this kind of increasing polarity where we are, put this whole thing up here, over here. If you do the little subtraction and you get an electronegativity difference of less than 0.4 or less, even if it's 0.4, you're like, yeah, that separation, that partial negative, partial positive, it's basically negligible. To the point that we're going to call that actually a covalent, a pure covalent, non-polar. So anytime you see pure covalent, think non-polar. Pure covalent, i.e. non-polar bond. Beyond 0.4, it's got a degree of polarity. And I have a thing to kind of talk about the words we use to increasing polarity. See where I said I did 1.7 before, now it's 1.8? Okay. At some point, the atom that's got a higher electronegativity is going to say, forget this sharing bit, I want it. Okay. And I'm going to become an anion, and the thing I steer still from is going to become a cation. So this is, I think, the slide that I had in Chem 1. Electronegativity difference of 0, it's a nonpolar bond. 0.5, which is, I guess it's above 0.4. 0.5, then it's polar, but just weakly so. 1, that's polar. 1.2, strongly polar. 1.7, electron is transferred. 1.7 and 1.8. So those first 4 are actually all types of covalent bonds. And what I'm hoping you remember is covalent means electrons are shared. Covalent means electrons are shared. Ionic, electron is transferred. Okay. So this isn't a very good Lewis structure of carbon monoxide. It's actually not a Lewis structure because it doesn't show like the lone pair electrons. I'm thinking carbon monoxide is a double bond or something. But if we just look at the arrangement of atoms of carbon monoxide, it looks like this. If we look up the carbon atom, see which one's more electronegative. Oxygen. Actually, since they're in the same period, we can see that oxygen is. Yeah. So that's not so surprising. So you're going to want to be able to kind of do that sort of thing. We could go ahead and draw in the vector, and it looks like this. Okay. Again, kind of, we start at the partial positive end. We end, and it's a physical sort of thing because so position of this sort of vector thing is showing you the direction, and the length is showing you the magnitude. Because what are we at? See, is it relatively polar? Let's see, look at carbon 2.5, 3.5. You're looking at a delta chi of 1.0.
So, what is that vertical line?
Yeah.
What is this?
The one going up and down, vertical line.
This it's part of the vector thing. It's part of showing you that polarity. It's part of showing you the polarity,
Okay.
and it's kind of nice because the up and down line, think of it as kind of a part of the plus. Yeah, part of the plus.
So that's what that is basically.
Mm-hmm. Yep. Yep. So, of course, electronegativity difference between the 2 chlorine atoms is kind of like over here. There is none, so it's a pure covalent bond. Pure covalent bond, and it's nonpolar. Hydrogen chlorine, there is definitely a degree of polarity. And it's not a mistake to show that chlorine kind of big like that. They're trying to show that on purpose because its electronegativity is greater. So the electron cloud around it is more. And then when we get to, of course, table salt, sodium chloride, the electronegativity difference, what do we got here? The chlorine is 3, sodium is, sodium? Oh, there, yep, 0.9, so you're at 2.1? Yeah, 2.1 electronegativity difference. So electron is transferred from the atom with the lower electronegativity to the one with the higher electronegativity. This is kind of showing you the visual sort of in color. So where you see yellow, think that that's neutral. Where you see red, think I'll go this way. Where you see, where we see red, that's partially negative. Where you see blue, up to kind of this dark color, these 2 colors look similar. Blue, then that's partially positive. So there's Cl2. Notice that the electrons are distributed evenly. They're shared equally. You would expect that. HCl, not so much. The chlorine atom is starting to turn kind of this color, negative. And I don't know, I can't detect it much, but we expect the hydrogen to be partially positive. And then in the case of sodium chloride, electron is entirely transferred, so that chemical bond is not covalent, it's an ionic bond. But you can see that the chlorine is now a chloride ion, so it's very negative. And the sodium has lost an electron, so it's very positive. I'll show you those. Think of that buzzing around, that's your electron cloud. Of course, we have 7 elements that like to be diatomic. So we have oxygen, hydrogen, remember that Hofbredical thing? So those are both diatomic elements. Must be another class in here. I don't know. It's like everybody wants to stop and be a
You're like, man, I wish I was in that class.
I know, right? Partially negative fluorine, partially positive hydrogen. Fluorine has the higher electronegativity, and here an electron is transferred entirely. I think you get that. Actually, this is a good place to stop. Anytime it uses the word "do not confuse," it's time to stop. But don't forget what we have talked about, because we're switching gears on Wednesday. And your lab is Thursday.
I have intro to biology next.
Oh,
Do you know where that is?
It's over here.
is it in 501?
When I had the night class, it was that room, like right at the end of the hallway on the wall.
511?
Yeah, I think it's
But-
Nebraska.
Yeah.
She likes 511.
We have intro biology.
Yeah.
You have intro to biology with Mr. Russell. I have Mr. Jones.
She's good.
Yeah.
And she's taking astronomy with me.
Oh man.
Yay, Allison. She's like doing the science thing.
I wish I could have. You know, how those two